Dear students, in this video, let's talk about wave function, and certainly wave function is it's a state vector, and it's the basic tool to calculate the uh, to have any information that we can have about the microscopic particles. Now, to start with, we can talk in terms of waves. Suppose we have water waves, right? And here we talk about the height of a wave and the waves that propagate on the surface of the water. These are water waves. We say that they are water waves, and then we have another class, say for example, light waves. Light is a wave, and it has electric and magnetic field associated with it, and these electric and magnetic fields vary with the span of time. And then talking about matter here, like matter waves. And matter waves, the waves that are associated with the matter at microscopic level, their state can be talked about in terms of a wave function. To be very literal here, in terms of wave function. So here we have electric fields and magnetic fields, the varying electric fields and magnetic fields. And here uh, we have the height. I mean, height of water waves on the surface. Height on surface. And to be precise, this wave function is represented by psi, right? And psi is a vector. It is a state of a vector, and psi is basically related to the probability of finding a particle. And it was I think Max Born. It was Max Born uh, who uh, who put the idea forward, for the first time. Uh, he put the idea forward for the first time uh, that that the wave function that we have, the wave function psi, it indicates the state of the particle, right? It indicates the state of the particle, right? And however, this psi it does not have the direct physical significance. And for this, there is a simple reason that why psi cannot be interpreted in terms of an experiment. I mean, the probability that something be in certain place at a given time must lie between, say, 0 and 1, right? And the object is definitely not there at 0, and the object is definitely there at 1, right? These are the two situations that one can think about, right? So an intermediate probability. Suppose the probability that we are able to obtain by making some calculations on psi. Let us assume that that comes out to be zero point 0.3. Now, what does it mean? What does it mean? It means that there is nearly 30% of chances of finding the object, right? Uh, However, so here we have a probability of 30% of finding the particle. However, the amplitude of the wave can be negative as well in this kind of situation where we are directly making the measurements on psi, and and if if on making a measurement the amplitude comes out to be negative, uh, uh, then we will certainly have a negative probability, and negative probability, uh, uh, that means minus zero point 0.3, and it is meaningless. Hence, psi by itself cannot be interpreted. It cannot be an observable quantity. So psi itself cannot cannot be an observable quantity, because on making measurements we will come up with the negative values of psi, and if psi comes to be negative, that means we have negative probabilities, and these negative probabilities do not have any meaning in physics, right? So here at this juncture, I mean, at this point, what we say is that that because of this, the square of the absolute value of wave function, psi is a complex number, right? Uh, the square of its absolute value, I mean, of this wave function is considered and is known as probability density. So psi, okay, we said it doesn't it doesn't have any physical significance, but psi square does have, and this psi square is what? It is probability density, right? Psi square is the probability density, and the probability of experimentally finding the object that is described by the wave function psi at the point, say x, y, or z, at the time t, is proportional to this. It is all proportional to psi square, right? Now, if we have the if we come up with small value for this psi square, if its value comes out to be small, then what it means is the probability of finding that object or particle here is very less. And if it comes out to be big, then we'll say that the probability of finding that particle at that instant, at that position, is large. Now, as long as this psi square is not actually zero, uh, that means somewhere, however, there is a definite chance, however small, of detecting it there be. And this is what Max Born first made in his interpretation. It was in 1926 probably, that if the probability is is less, we cannot rule out it. That means there is some probability that the particle can be at that position, even though the magnitude of psi psi star is extremely small. Now, if we know the momentum of a particle, say for example, we can find the wavelength of the associated matter wave by using the equation, the de Broglie equation we have. What's that equation? That is lambda is h by mv, where lambda is the wavelength, h is the Planck's constant, and mv is the momentum. We have now to realize how we can describe the amplitude of a matter wave. I mean, that's we have to find out just what it means, and we have to find out the pros uh, in achieving such kind of thing. Now, let us assume that we have a particle of mass. Its mass is m, and say, for example, it's traveling in x direction with no force acting on this particle, right? So it's moving around x, and it does not. There's no force acting on this particle. If that's the situation, it's moving around x, and no force is acting. No force is acting on it. No force is acting on it. Right? Now, if that's the situation, then according to Schrödinger, the wave function that we have, the wave function psi of x at an interval of time t, this wave function is psi naught e to the power of I times kx minus omega t. So if we have a particle of mass m, and this particle is moving in x direction, and no force is acting on this particle, then the motion of this particle, then the motion of this particle can be described by a wave function, and this particle is moving in the positive direction of x, and that can be given by this equation. Here, this psi of x and t, it is a complex. It's a complex number. It's a complex number, right? So this is how we can write down a particle moving in x direction with no force acting on it, and we are very aware about the symbols, like k is here propagation vector, and it is 2 pi upon lambda, and this omega is the angular frequency, and it can be correlated with linear frequency as 2 pi nu. Now, if we proceed on and and if we proceed on and we start talking about probability density, because as we already defined, as it was defined by Max Born, that probability density is basically psi star, the magnitude of psi, square of the magnitude of psi, and this square of magnitude of psi is basically psi star, and psi is a complex number, and psi star is the complex conjugate of this complex number. If for example I have a complex number, a plus iota b. Let us assume it's the wave function psi. If I take its complex conjugate, it will be a minus iota b. Now, if I multiply the two in order to get the psi star, I will come up with a result where I'll find the overall value of psi star is a real number, and certainly that number can be used. That number can be can have can have the physical significance. It does have the physical significance. So here, this is what this is probability. This is probability density. Now we have taken a particle who is moving in the positive direction, and its wave function is it is like this: e to the power of iota kx minus omega t. Now, this is my wave function psi for a particle that is moving along x, positive x direction, and no force is acting on this particle. And I can take its complex conjugate, that is psi of x and t. That is, we can have a complex conjugate of psi naught as well, and then we will have e to the power of minus iota times kx minus omega t. So here we can measure psi of xt and psi star of xt. So what we are going to get here it is psi e to the power of I kx minus omega t, then psi e to the power of minus I kx minus omega t. And we can immediately obtain here psi naught scal, right? And precisely, if this value comes out to be maximum, there is a strong possibility of presence of particle there. For maximum value, the possibility of finding the particle is maximum, and if we get its value as small, at that position, we have less possibility of presence of what is called as presence of the particle at that point, right?